Okay, so want to talk about Oracle problems. So first, I'll introduce the setup. By Oracle, I mean a black box or a function. So basically, it's a box, and the box hides some function, and we can't open the box. We can only access the box via queries. So classical query just computes the value of the function f of x for some x. But the quantum query is a unitary gate. So for example, it could be the shift oracle. The shift oracle just acts on two registers, x and a, and its action just shifts the second register a by f of x. So that computes the function. Now, by an oracle problem, I mean that we have the following setup. We have a promise which functions may appear inside the black box. And we have some classification. So the set of allowed oracles is partitioned into disjoint classes. For example, here we have 7 allowed functions, and they're partitioned into classes A1, A2, and A3, where here A and 1 are constant functions, A2 are polynomials, and A3 are trigonometric functions. So we have a unitary gate UF for each f, so it could be the shift oracle or maybe another type of unitary. And this is not very standard, but here we also assume that we have some probability distribution defined on the set of allowed oracles. So let's say, for example, in here, maybe sine x can appear with probability 1 over 5, and x squared probability 1 over 6, and so on. And the classification task is to classify the oracles. So we want to find which class, what is the unique class to which f belongs. For example, here we have some black box, and in the black box we have some function, and we want to find whether the function is constant or a polynomial or a trigonometric function. So for example, Doi-Josa is a very well-known example. So here we're promised that the function f takes as input n bits and outputs 1 bit, and it's either constant or balanced. So here the two classes are AC and AB. AC are the two constant functions, so always 0, always 1, and AB are the balanced functions, where balanced means that the function outputs 0 for exactly 1/2 of its possible inputs. So here we assume that UF is a shift oracle. And we know that we have a quantum algorithm, the Doi-Josa algorithm, that finds the class A, B, or AC with probability 1 using just one oracle query. So now for motivation. So we know that in many cases, quantum algorithms are better than classical ones in solving these classification tasks. So as we just said, the Doi-Josa solves the Doi-Josa problem with just one query. But any classical algorithm would need an exponential number of queries. So here we have exponential quantum advantage. But the advantage is not always exponential. It could be polynomial or maybe constant, maybe even no advantage at all. It could also happen. So we get this overarching goal, which is to characterize the problems for which we have huge quantum advantage. Where by huge, we usually mean more than polynomial. So if you can do that, then this would illuminate what we can and can't do with quantum computers. So this is an ambitious goal. It's probably very difficult to do in general. But I believe we can sketch some roadmap to attain this goal via simpler questions. So the questions are, what are the features that lead to quantum speedup? And what makes a quantum algorithm good? And also, can we find the best quantum algorithm for a specific classification task? So for this last question, we can restrict it and look at a very simple, or the simplest possible instance, which is, what if we only allow one query? So what we want is to find the best single query quantum algorithm for an arbitrary classification task. And by best here, we mean that we want the highest possible mutual information between the correct answer and the output. So this is not a very standard figure of merit, but it is a figure of merit. It does measure the performance of algorithms. So this is what we will use. So what is a single query algorithm? Well, it always has this form. We prepare some initial state psi naught, perform some interrogate v, then the Oracle query UF, another interrogate W, then we measure in the computational basis. We can only do one query, so this is essentially everything we can do. So the question here is, how do we choose V and W such that we optimize the information about the class AJ contained in the measurement outcome here? So here's the key idea. The key idea is an analogy between the problem I just mentioned and a quantum communication task. So first, what is a task? A task is very, very basic. We have Alice and Bob, and they agree on some finite alphabet, script J. And Alice wishes to send some message to Bob. And the message is an element of this alphabet, a letter. So what they do is Alice chooses J based on some distribution. So it's a random variable. And for each J, she prepares some quantum state sigma J, sends it over to Bob, and then Bob measures it, and he needs from his measurement outcome to deduce Alice, the letter that Alice actually meant to send. So in the setup, what they want to do is to maximize the mutual information between J and Y, where Y is the measurement outcome of Bob. So now what we have here is like this. We take any algorithm of this form, we cut it here at this point, cut it into two pieces, and then we get a protocol for this communication task. So here the alphabet script J is the set of Oracle classes, and the protocol works as follows. So if Alice draws random element small j, then she then draws a random f out of the class AJ, and then she does the first three parts of the algorithm. So she prepares psi naught, she does v, and then she performs the query UF. So effectively what she has at this point is a mixed state sigma j, which is essentially the computer's state here, but a mixture over all possible f's in AJ. So that's why it's a mixed state. Then she sends sigma j to Bob. Bob performs W, measures in the computational basis, and gets some bit string Y, which is also a random variable. So what we got out of this is we can use normal results about these communication tasks. So in particular, we know that IJY is bounded by a quantity called chi. This is Holevo's bound, and this chi is called Holevo's quantity. It's a function of all of those sigma j's. And we can say that the optimal single query algorithm has this form. You can describe what it looks like. So we need to choose V in a way that maximizes chi. And then we need to choose W such that it would minimize the difference between chi and IJY. So W cannot change chi. So once chi is fixed, I want to minimize this difference, and then this would maximize IJY. And it turns out that this difference is a form of quantum discord. So we also get a description of algorithms that always succeed. An algorithm always succeeds if and only if this mutual information IJY equals chi, which equals the Shannon entropy of J. So to obtain this second equality, what we need to get is that the sigma j's are all orthogonal. And this just means that the Hilbert space splits into this direct sum of orthogonal subspaces indexed by J. And to get this first equality here, what we need is for the computational basis to respect this splitting. So that's it. That's how every algorithm that always succeeds looks like. So we have a few further results, which I'll state briefly. I'm sure you're all hungry and want to go have lunch. So when we analyze like this IJY, a few quantum information quantities just pop up. So I mentioned the whole level quantity chi, but there's also von Neumann entropy and quantum discord and quantum coherence and irrealism. So what we did next was to demonstrate how these quantities vary throughout stages of running some quantum algorithm. So this essentially this allowed us to see that our results really hold, to verify that they hold, and also to gain some insight, some intuition about what good algorithms look like, which I'll show an example soon. Also, all of these results hold not only for single query algorithms, but also to multiple query ones, provided that the queries are all done in parallel. So we call such algorithms non-adaptive. So here's an example for a Doi-Jaza with n equals 4. This is the circuit. So initial state, this is the V, right, the first unitary. Then the query UF, the second unitary W, and then measurement in the computational basis. So what we did was look at these quantities in 3 stages. So what it means basically is that what happens if we stop the algorithm here and measure at this point, or let it run to the end and then measure at the end. So this is the pre-query, post-query, and final stages. And for each one, we computed the information theoretic quantities. We have Shah entropy of Y and von Neumann entropy of rho Y and coherence, conditional entropy chi that I mentioned before, mutual information, and the discord. So one thing we can see here is that most of the quantities are either monotonically increasing or decreasing, but the discord is not. So intuitively, we can say something like, we need to build up the discord, and then we kind of use it as a resource, and it decreases to increase the IJY, which is what we really want to maximize. So this gives us some picture about what good algorithms should look like. So yeah, to conclude, we got this bridge between quantum computation and communication, and our results also highlight the role of these information theoretic quantities in constructing good quantum algorithms. What we'd like to do next is first generalize our results to include also adaptive algorithms. So adaptive here just means that multiple query, but not necessarily in parallel. So for example, Grover's algorithm is adaptive in this sense. And a couple of undergrad students are working on a project exactly on this. They already have some nice results. And also, it could be really interesting if we can use these results to improve lower bounds on query complexity. Another thing is this would be really great if we could do something similar for classical algorithms. Because if we can do that, we can compare classical and quantum cases and then study quantum speedup directly. Finally, it would be nice to apply this framework to alternative models of computation. So it could be adiabatic, one-way, topological, maybe some others. That's it. Thanks for listening.
Thank you, Amit.
Thanks for the talk. So I have a question. I mean, all the examples that we know, that there is an exponential advantage, these are just periodic functions on a group, on an abelian group, in fact. Right? And then you use Fourier transform on a group, and that's what solves all these problems.
I'm not sure I agree with this. So Doi-Jaza is not really.
It's group. It's the group Z2 to the power n. That's Doi-Jaza. It's always a Fourier transform on a group on
That's not, from what I know, that is not accurate. So Deutscher,
It is the group Z2 to the N.
the Deutscher problem is not the hidden subgroup problem for n greater than 2. For n equals 1 and 2, Deutscher is the hidden subgroup problem. Right?
It's the hidden subgroup for Z2 for the simplest case, Z2 to the N to the general case, and then abelian group Zn to the short case. I mean, we can discuss it.
Okay.
It's always the abelian group, it's not the non-abelian one. My question, any periodic function,
Uh-huh.
my question is whether this actually gives an indication of something which is not periodic function, which is, the oracle is not a periodic function, so that there is a chance also there. It's a difficult question, I don't know if you thought about it, but,
So we did do an analysis of the Shor-Kitaev algorithm for the abelian hidden subgroup problem in general, not for a specific instance, but in general. But yeah, exactly. But that's not what you asked. So you're asking whether you can say something about oracle problems for.
whether there is an indication in your approach for something which is not a periodic function. That's my question. I would say it's a difficult question, but I don't know if there is any indication.
So for now, we can't really say anything about that because what we can do with this approach is to analyze existing algorithms. Okay. So we can. I guess you can ask what is the best non-adaptive algorithm that uses T-query for an arbitrary. That we can do, but I don't think we examined anything like this. Yeah.
I may comment about that because I have some examples in my mind. Maybe they are not the best. First, I think there's the example of the hedral group. So
it's not working. It's only for the normal subgroup. It doesn't work for, but that's like an abelian problem. It's only the normal subgroup part.
And in addition, we've examined index 2 and hidden subgroup, which may not necessarily be abelian.
Yeah, I think it doesn't have to be abelian. I actually need to think about it. I'm not sure if it has to be abelian or not. Maybe not.
We've started to devise an algorithm for a specific case of index 2 hidden subgroup of non-abelian group.
Okay, so it's interesting to discuss. But the problem is, of course, because the Fourier transform on abelian group doesn't work.
Right.
And you need to expand in the irreducible representations. And this was like the stumbling block for many years.
Yeah,
so there is an interesting idea in it.
But when you say it doesn't work,
it means you cannot get an exponential advantage.
Because it's difficult to do the Fourier transform.
It's not difficult. The Fourier transform on non-abelian groups is an expansion in all the irreducible representations, not only the abelian ones.
Right.
It's not in the characters.
Yeah.
And when you do that, it fails, except for the normal subgroups of, let's say, the dihedral.
Yeah. No, but when you say that you can't get an exponential advantage, I think that it's in terms of gates, not queries. I think you can maybe you can still get a polynomial query number, a polynomial of queries, right? Because the best algorithm for a finite group.
But you mean the size of the size exponential of the
Size of the
circuit is exponential.
right, yeah.
That's not what
In terms of query complexity, you don't see that. If you only discuss query complexity, then you have a polynomial number of queries that's good for you. Yeah, but I agree. It's not really. Maybe it's not practical. Yeah.
Right. If it's exponential, I think you can do it. If you give me an exponential circuit, then I don't think there is an issue. The issue is not an exponential.
No, of course. But I mean that in query complexity, you only cover the number of queries. So if you can do with a polynomial number of queries, then it's kind of
Okay. We can discuss it.
yeah. Okay.